Swayam Prabha. Digital India. Educated India.
Okay, so you see, we have these global theorems on plane curves, okay, of which the Jordan Curve Theorem and the Hopf's Umlaufsatz are not easy to prove. Okay, they involve methods of topology and analysis, for example, complex analysis. However, there is this isoperimetric inequality which I explained to you about this one and the next one, which is the Four Vertex Theorem. These are all global theorems about curves which can be, they can be proved with elementary knowledge of differential geometry. So let me go ahead and tell you something about the Four Vertex Theorem. Okay, yeah. So the Four Vertex Theorem. So the idea of this theorem is that if you are looking at a simple closed smooth regular curve, okay, then basically it's a curve which starts at at a point and then comes back, and it's smooth throughout, all right. And if you think of it very naively, it means that to come back to a point, you have to at least turn at 4 places, okay. And of course, the one thing you have to remember is that if you are going on the curve, a part of which is an arc of the circle, then it is very clear that at every point of that arc, you see, you are continuously turning. Okay, so you want to exclude that case, and but otherwise, if you want to think of this in differential geometric terms, the idea is that you have to use the concept of vertices. So what is a vertex? A vertex is a point where the sine curvature function has a critical point. Okay, that means the sine curvature function, the derivative of the sine curvature function is 0. Okay, and in particular, it could mean that the sine curvature is either attaining a local maximum or a local minimum. Okay, so what the Four Vertex Theorem says is that you take a simple closed smooth regular curve on the plane, then it has at least 4 vertices. Okay, and in fact, there's to be more precise, what it says is that there will be at least 4 points where you'll have local maxima minima, and it will turn out that there will be at least 2 local maxima and there will be 2 local minima for the curvature. Okay, and of course, where the curvature function has a local maximum or a minimum, these are going to be among the critical points, because the points of local maxima minima are certainly critical points. Okay, so so that is a theorem. All right. So this theorem was proved by Shamadas Mukhopadhyay in 1909. Okay, and then there were so he proved it first for convex curve. Then it was proved for a general curve by Adolf Kneser. Okay, and then it took several decades before a converse was proved. So the converse will be that if you have a continuous function which is supposed to be the curvature function of a curve, and this continuous function has at least 4 local maxima minima, of which 2 are local maxima and 2 are local minima. then this function is actually, the curvature function for a simple closed regular smooth curve. Okay, so that is the converse. So the converse was proved for strictly positive curvature several decades later, and then very recently, which is in the 2000s, I think it was proved in generality. So this is about 100 years story where this theorem and its converse have been proved. Okay, and of course these kind of statements have been generalized to curves over on surfaces, and there are generalizations to surfaces also, and so on and so forth. Okay, so let me write this out. A simple closed regular smooth curve. Of course, we are only talking about plane curves, so it's a plane curve. Okay, has at least 4 vertices. In fact, has at least 2 local maxima and at least 2 local minima for its sign curvature. Okay, so this is the theorem, and a full converse also holds. Okay, so I will just let me just write that in the as a remark, but we will not prove it. Remark: a full converse holds. Okay, so so you see the so here it's important that I have to tell you that because the curve is it's regular. Okay, so it has a unit speed parameterization, and therefore it's in the unit speed parameterization, its speed, the velocity vector is a unit vector which is c1. Okay, and mind you, want to talk about the curvature of the curve, so this must be c2. Okay, and therefore the parameterization is c2. So if you take the derivative of the parameterization, which is the velocity vector, that has to be c1. So it's a c1 unit vector, so it has a turning angle, and the rate of change of the turning angle is the sign curvature. Okay, so so the sign curvature makes sense. Okay, and the point is that the sign curvature, the derivative of the sign curvature can vanish at several points. These are the critical points of the sign curvature, and among those points are the points of local maxima minima. And the statement is that there are at least 2 local maxima and 2 local minima, and these already account for 4 vertices. Okay, so there are at least 4 vertices. So the way this theorem is proved is by trying to show that a curve with lesser than 4 vertices, namely with 3 or 2 or just 1 vertex or without a vertex, is not possible. Okay, and finally it will reduce to the 4 vertex case. I mean, essentially it will reduce to the case when there are only 2 vertices, which corresponds to a local maximum and another which corresponds to a local minimum. Okay, you can use basic calculus to show that if you have so if you take any 2 local maxima, in between there has to be a local minimum. Okay, and between any 2 local minima there has to be a local maximum. Therefore these local minima and local maxima will occur alternately, okay, on the curve. And the existence of at least one local maximum and one local minimum. In fact, the truth is the existence of even one global maximum and one global minimum comes from topology. That a continuous function on a compact set, if it is real valued, has a global maximum and a global minimum. So, at least one global maximum and one global minimum are guaranteed. So, there are at least two vertices, okay, and you have to show that there are four, okay. But if there is one more than two, then out of these three, two of them are going to be of the same type. They must both be local maxima or both local minima, and therefore in between them, these two, which are both local maxima or local minima, there should be another local extremum of the opposite type, okay. Therefore, the only case you have to worry about is there is exactly one local maximum and one local minimum, which is also a global maximum and a global minimum, and you have to contradict that such a case cannot occur. I mean, okay. So you have to show that, okay. And the important thing is that the simplicity of the curve is very, very important, because if you remove the simplicity of the curve, you can get a curve of that type. So if you take a curve of this form, so let me give you a counter example for case when the curve is not simple. Is the following situation. So you look at this kind of a curve. So this is called the limacon. So this is the so it's a curve like this, okay. Now this is given by the equation r is equal to, if you want, a into 1 plus 2 cos theta, okay, in polar coordinates, okay, and 0 less than or equal to theta less than or equal to 2 pi, right. Now you see, if you put you can see that if I put theta equal to 0, all right, I get r equal to 3a, okay. So basically I will get this point, this is 0 comma 3a, or rather 3a comma 0. This is 3a comma 0, okay, and this corresponds to theta equal to 0, all right. Then you go all the way to this point. This point corresponds to theta equal to 90 degrees. Mind you, these are polar coordinates, all right. So here theta equal to 90. If you put theta equal to 90, you will get r equal to a. So this point is 0 comma a. So this corresponds to theta equal to pi by 2, okay. And then of course, if I put theta equal to 3 pi by 2 also, I am going to get r equal to a. So that is going to be this point. So I will get 0 comma minus a, okay. And I want you to understand that the r is the distance from the origin. So this point is 0 comma a, but the distance from the origin is a. So this length is a. This length is also a, okay. And this whole length is 3a, okay. So this corresponds to theta equal to 3 pi by 2, okay. And what happens is that when you come to this point here, okay, yeah, for this term to vanish, I must have cos theta equal to minus half, and that is what that is 2 pi, and that corresponds to these two angles which are tangent at the origin. So basically what happens is that you see, so at the origin you have this angle and you have this angle, and these angles are this is 2 pi by 3, and this is well, I think I should not draw it like this, and this whole angle is 4 pi by 3, and so that those correspond to this point. So that point is a self intersection, okay, and this point here should correspond to pi, Okay, see, this is part of several curves which start with something like a flattened pier on one side, and then this flattened thing, it's like an oval thing with one side more flat, and this flat thing starts coming inside, and it at one point forms a cardioid, and then after that this cusp in the cardioid develops a loop and becomes something like this. So it's a continuous family of curves. So the general equation is r is equal to a plus b cos theta. That is the general equation. See, the point about this curve is that you can write so this curve, you see, you can write a regular parameterization for this. Okay, and if you notice for this curve, what will happen is that at this point the circle of curvature will be the minimum. Okay, I mean it will be smallest. So the radius of curvature is the smallest, so that is the maximum curvature. And at this point, it will be the largest, and the radius of curvature will be the largest, so the curvature will be the smallest. So you see, these are the only 2 points which are vertices. So at this point where it hits the x-axis farthest from the origin, there you have maximum radius of curvature, you have minimum curvature. Then as you move like this, okay, all the way up to here, when you come to the this inner point where it hits closer to the x-axis, all the way there, the curvature is increasing. It's continuously increasing, and it gets a maximum only here. Then again from here, when you go back like this, it starts decreasing and comes to this the curvature becomes least there. Okay, so there are only 2 vertices for this curve, and it therefore doesn't satisfy the Four Vertex Theorem. The problem is that you have allowed one intersection, one self-intersection. Okay, and somehow of course there's something more to this. It's not smooth actually in the topological sense, because at the origin there is actually a node. Okay, and but simple, the moment you put simple, there are never going to be any self intersections. So you are not worried about topologically singular things. All right. So this regular, the problem with a definition of regular is that you are always trying to do regular parameterization for a simple curve. The regularity and geometric regularity are the same for simple curves. The moment the curve has a self-intersection, it's topologically singular, okay, because there is more than one tangent, but that doesn't prevent it from being regular, because you can get a regular parameterization even at a node. So this is that case where it is topologically singular. Okay, there are 2 tangents at the origin, so it's not smooth in that sense. On the other hand, it is actually regular because you can get a regular parameterization. This itself, this equation itself can be used to give a regular parameterization. You can check the velocity vector is never 0. So this is a regular parameterization. Okay, so you should remember that regular parameterization and topologically smooth in the sense that geometrically smooth, that is okay for non-self-intersecting curves. Okay, when the curve self-intersects, at the point of self-intersection, you can still have for such a curve regular parameterization. What will happen is that the same point will come on 2 branches of the curve corresponding to 2 different parameter values. Okay, and that parameterization can be regular. But in spite of that, if you look at it topologically, it's not smooth because there are 2 tangents there. There is no well-defined tangent. Okay, but if you take each branch, then each branch is smooth and it has a well-defined tangent. Okay, so that is something that you have to keep in mind. So so let me get back to the so now what we will do is let's try to look at the proofs of these statements. So what I will do is the following thing. Let me first try to look at the proof of the isoperimetric inequality. See, the basis of the proof is what is called as Wirtinger's inequality, and this is very simple case of something that's very general, called the Sobolev inequality, which is a very hard inequality in functional analysis. Okay, so so let me tell you about that. So let me write this here. Proof of the isoperimetric inequality uses the following. So this is called as Wirtinger's inequality. Okay. So this inequality is essentially an inequality which says that the root mean squared value of a function cannot exceed the root mean squared value of its derivative, and when you get equality only in the case of constant multiple of the sine function. Okay, it's a very beautiful inequality. So let me write that and explain. So you see, let capital F from 0 pi to R be a so what do I want C1 function. So it's first continuously differentiable, okay, such that f of 0 is equal to f of pi to 0. So it is 0 at these ends. So one standard example that you can think of is a sine function. Sine 0 is 0, sine pi is 0. Okay, and then f RMS less than or equal to f dash RMS with equality if and only if f of t is equal to d into sine t. Okay, and so what does this root mean squared velocity? I mean, so this root, I think you must be familiar with this root mean square velocity. Okay, it is the square root of the mean of the squares. Okay, so here what does this mean? See, what I have to do is that I have to take the squares and then I have to take the average, but you see these are over all the points in 0 pi. So that means you have to sum all the values over the points of 0 to pi, which amounts to an integration. And then you have to, when you take average, you have to take the mean value of the integral, which means you have to divide by the length of that interval, which is 1 by pi, which is pi. So you have to multiply the integral by 1 by pi. Okay, so and then you have to take, of course, the square root. The square root is anyway not a big deal. So let me write it out. You see, you take f of t squared. Okay, then you integrate from 0 to pi and put dt. This is the sum of the squares. The mean is 1 by pi, which is you have to do. This is the mean value of the integral. Okay, and then you take the square root of that, and this is less than or equal to the same expression for the derivative. So it's 1 by pi integral 0 to pi f dash squared of t dt and square root of. Okay, where of course f dash of t is just df by dt. So I think I have changed, unfortunately, from small f to capital F to small f. So let me correct it. So notation. So you see, you take f capital F defined on 0 on the closed interval 0 to pi, and it's a C1 function. So its derivative is, the first derivative exists and it is continuous, and the function is 0 at the endpoints. Then the inequality is capital F sub RMS is less than or equal to capital F dash sub RMS, where RMS is the root mean squared velocity. I mean, is the root mean squared value. So this is defined like this. So let me, unfortunately, I used capital F. So you see, therefore this is a statement. Okay. Now, of course, this is equivalent to, if you look at it, this is equivalent to simply I can clear the square roots and I can clear the pi also. So basically, it amounts to integral 0 to pi f squared t dt is less than or equal to integral 0 to pi f dash squared t dt. So this is a statement with equality if and only if f of t is equal to d times sine t, d a constant. Okay, and so of course you can check the case of example if you take g of, so if you take f1 of t to be d sine t, then you see f1 RMS is so let me not get into this. Let me just write the integral. So integral 0 to pi f1 squared t dt is going to be integral 0 to pi d squared sine squared t dt, and so I will get I will get d squared, and I think the if you evaluate the remaining of the integral, I will get I'll get pi by 2. Okay, it's going to be 1 plus cos 2t, 1 minus cos 2t by 2, and you integrate it, you will get 1 integral of 1 by 2 dt is the pi. So you will get this, and if you do it to the derivative also, integral 0 to pi f1 dash squared t dt is going to give you it will be d cos t, so it will be integral 0 to pi d squared cos squared t dt. That's also going to give you a d, why did I put it, that's right, yeah, d squared into pi by 2, and these two are equal. Okay, so for this function it is equal, and of course notice that this is of course c1, it is actually an analytic function, infinitely differentiable, and of course f1 of 0 is 0, and so is f1 of pi. So this is a standard example, right? But the result is that this is always true, that the integral of f squared is bounded by the integral of the derivative of f whole squared, and the equality holds only for the multiple of the sine, constant multiples of the sine function. Okay, that is the inequality. Okay, so so how does one prove this? See, we focus on this thing. You want to show that your f of t is d times sine t, and if you for the moment believe that you see the sine t, if f of t is going to be sine t, then sine t vanishes only at 0 and pi, nowhere in between. So essentially what you're trying to show is ft by sine t is a constant d. Okay, and the problem with ft by sine t is only when t is 0 or t is pi. So the trick is you look at ft by sine t, okay, and show that ft by sine t is a constant, okay, and that too very indirectly. And what is the issue at t equal to 0 and t equal to pi? You see, at t equal to 0, f0 is also 0, sine 0 is also 0. Therefore, by L'Hopital's rule, limit t tends to 0 plus ft by sine t will be just f dash 0 by sine dash 0, which is cos 0, which is 1. So it will be just f dash 0. And similarly, at t equal to pi, okay, again you can again apply L'Hopital's rule. So the point is that even at the endpoints, this function is ft by sine t is well defined. Okay, so so I'll just say proof is we need to show that g of t is equal to f of t by sine t is constant. Firstly, g of t is defined on 0 pi as t tends to 0 plus limit t tends to 0 plus ft by sine t is actually f dash 0 by sine dash 0, and this is because f of 0 is equal to 0 and sine 0 equal to 0, and you are using, of course, L'Hopital's rule. I think let me not write the okay, and this is just f dash of 0, sine dash is cos 0 is 1, okay, and as t tends to pi minus, limit t tends to pi minus ft by again sine t is going to be just f dash of pi by sine dash of pi, okay, and I'm going to get sine dash is cos and cos pi is minus 1, so I'll get minus f dash, okay, and of course these are well defined values. Therefore, so G is defined on 0 pi, okay, and is also C1 there. So there is no problem about the endpoints, okay, and so you have a nice function G. You are trying to show it's a constant, and so and more generally, so here I must add that you want to show this for the extreme case, namely when the inequality is an equality, okay. So let me say that here we need to show that in the case of an equality, okay, G is a constant, okay, and so you see this so that is a motivation for defining this function G, okay, and then the point is that you use this G carefully, all right. So you see, but in general, you have to show that there is an inequality. So what you have to show is that you have to show that the integral of f squared is less than or equal to the integral of f dash squared. So if you bring everything to one side, you have to show the integral of f dash squared minus f squared is greater than or equal to 0, okay, and so that integral has to be computed, all right, and there what you do is that you use this G that is that you get that is inspired by the case that you have to prove when there is an equality, all right. So this f is written as G of t sine t, okay, and then you compute this the difference here and show that the difference is non-negative, okay. So what we do is we do the following thing. We want to show in general that integral of integral 0 to pi f squared of t dt is less than or equal to integral 0 to pi f dash squared t dt, and this is that is integral 0 to pi f dash squared t minus f squared t dt is greater than or equal to 0, okay. And now you plug in this G that we have defined. So you see your f will be G sine t. So your f of t is G of t sine t, okay. So f dash of t will be, by the product rule, it will be gt cos t plus g dash of t sine t. So you plug it in here. So that is to show. So I keep saying here also to show integral 0 to pi. You compute this, which is here. So I take the square of this. So I'll get gt cos t plus g dash t sine t the whole squared minus, okay, this term here is just g sine t, So I'll get g of t sine t the whole squared. You have to show this greater than or equal to 0. Okay, but look at what this term is. If I expand this, I will get g squared t cos squared t plus g dash squared, g dash t squared sine squared t. Then I will get a 2 g of t, g dash of t sine t cos t. And then I have a minus g t squared sine squared t. So the left hand side is this. Okay, and if you look at it, the terms that we are interested in is these two put together. That's because you see you're trying to show this quantity is non-negative, and the integral of a non-negative function is always non-negative. So basically you have to worry about the integrand, and the problematic term is only this part. Okay, and as well as this one. Okay, and what you do is that you notice that if you differentiate this gt squared, you get a 2gt g dash t. See, the point is that in the case of an equality, you are trying to show that ft ft is constant times sine t. Therefore, that amounts to showing ft by sine t is a constant. That suggests that you can look at the function ft by sine t and call it as gt. That gives you the motivation for defining gt. Okay, so and this g is also well defined at the endpoints. And whatever you do with f, you try to do it with g by writing f is equal to g sine t. So then, so the motivation comes from there. Okay, so let us write this down. Here the LHS is integral 0 to pi. So so let me write this as g squared t cos squared t plus g dash squared t sine squared t plus 2gt g dash t sine t cos t minus g of t g squared t sine squared t. Okay, and of course I forgot to put dt here. And this is so as you rightly say, you combine these two terms. You combine these two terms, I'll get integral 0 to pi g squared t into cos 2t, and then you look at the third term where there is a 2 sine t cos t is sine 2t, so I'll get a gt g dash of t sine 2t. Okay, and whatever is left out is as it is. It's going to be g dash squared t sine squared t. So I end up with this, and this is the derivative of this is d by dt of g squared t into sine 2t. Is that correct? Sine is correct. So 2g so 1 by 2 g square t sine 2t, is it correct? So if you differentiate this, I will get g square t cos 2t into 2. That's all right. That's first term. Second term, I will get 2g g dash into sine 2, and the 2 will get cancelled. That's right. Yeah. So this is exactly this, and by the fundamental theorem of calculus, the first term is going to be 1 by 2 g square t sine 2t from 0 to pi, okay, and this is going to go away. So you have to only worry about integral, plus integral 0 to pi g dash squared t sine squared t dt, okay, and this is a non-negative function, and it's an integral of that, and therefore this is greater than or equal to 0. Okay, so that way, so you see the nice thing is that this g helps. Defining this g helps. So everything in F is written in terms of g, and the motivation for the g comes from the strict, the extreme case where you have equality. Okay, and when will you get equality? In that case, this has to be 0. This integral has to be 0, which is the integral of the difference, and that will mean that this term has to be 0. Okay, but the integral of a non-negative function is 0 means that the integrand itself must be 0. Okay, therefore g dash square t sine square t has to be 0. But you see, sine square t is not identically a 0 function. So only g dash squared has to identically vanish. That means g dash has to identically vanish, and that means g is a constant, which is what you wanted to do. Okay, so we get equality if and only if integral 0 to pi g dash squared sine g dash squared t sine squared t dt is 0. This is if and only if g dash, the integrand is identically 0 throughout 0 pi, and this is true if and only if g dash t is 0 throughout 0 pi, and that is true if and only if g of t is a constant. Okay, so that's it. So it's a pretty simple kind of calculation. Okay, the only thing to remember is that g that you have to use carefully, and the motivation for that g comes from the extreme case, which is the equality. Okay, so but in general, this kind of equality has a lot of generalizations, and it works in extraordinary generality. Okay, so it's a matter of so you just go to the web and search Wirtinger's inequality, and you will get a horde of papers. People, Wirtinger type inequalities itself is an area where people publish a lot of stuff. So if you make g into a complex function, that means it's a complex valued function of a real variable. So it will have a real part, it will have an imaginary part. Then whatever calculus you do, you have to split the real and imaginary parts separately and do it. So if you allow g to be complex, then this g dash squared will split into real part of g dash squared plus I times imaginary part of g dash squared into sine squared t, and then you get the two real integrals. Yeah, and again, the problem is that do I know that the real part of g dash squared is non-negative? See, the problem is so complex numbers don't have an ordering. Therefore, what is going to happen is that in general, if you evaluate a complex integral, you will only get a complex number, and so you cannot write any inequalities, first of all. So complex numbers are not ordered. So inequality doesn't make sense for complex numbers, except that any inequalities you write for complex numbers, you put mod. You have to put magnitudes, and you can write it for those things. So complex numbers, you have to be careful. Okay. So that's it. I mean, so now the next part of the proof is that you use this. So this is already, you see, there's a little bit of cleverness here. Okay, and then you have to use this cleverly to get the proof of the isoperimetric inequality. There again, it's a very clever trick. I mean, it's really crazy if you think about it. The way, at least I'm only following what is given in Presley. So you start with a constant and make it into an integral. Okay, so that is from a constant, somehow you are bringing in the function. You're bringing in the integral of course, when you integrate something, you'll get a constant. But the point is to go the other way around. From a constant, you cook up some integral, and that's just because you want it. And that's again, it's a very clever proof. And so I'll have to do that. So we'll do that.